Hey students, welcome to lecture number 11 of Linear Algebra 1. So last time we introduced the notion of a basis for a subspace, and today we want to talk about coordinates. So recall that the basis of a subspace V is a set of vectors b1 up to bm such that they span the space. So the subspace V is given by the span of these vectors, and these vectors are linearly independent. So here the notation is a little bit different than last time, because now I will use this notation today to denote the basis. So the difference to last time is that we will write now these brackets instead of these curly brackets, and the only difference is that we will now care about the order of a basis. So the basis b1, b2 is something different than the basis b2, b1. So last time we introduced, we just wrote it as a set, and the set b1, b2 with these curly brackets is the same, because in the set we don't care about the order. So this here as a set is the same, but this, writing this as a tuple, is not the same. And this we will use in the following, because we want to care about the order of these elements. Okay, so for example, if I'm in R3, then one subspace in R3 is given by planes, for example. So let's take the example where, let's say, V is the span of two vectors in R3. Maybe let's take 1, 0, minus 2, and 0, 2, 0. So these two vectors, they span a plane. And you can also check that these vectors are linearly independent in this case. So in this case, this B, so let's call this here B1, this B2, B1, B2, this is a basis of V. And also we learned last time that if I count the number of elements in a basis, that this is a dimension of the space. So in this case, the dimension of this subspace is 2. So the elements in this subspace, so the elements in this plane, are all linear combination of these two vectors. So for example, the vector, let's take 1, 4, minus 2. So you can ask yourself, is this vector an element in this subspace here? And the answer is yes, because this vector here is 1 times this vector plus 2 times this vector. So let's write this. So it's 1 times b1 plus 2 times b2. And today what we will introduce is the notion of coordinates. And what this just means is that if we fix a basis, like here, for a subspace V, and we have an element in this subspace, then these numbers here, which tells us how to write this element in terms of these basis elements, these are called the coordinates of this element x. And we will then introduce the notion of the coordinate vector of x with respect to this basis here. And because this is in a space of dimension 2, this will be a vector in R2. So this 2 here is exactly the dimension. And in this example here, what this vector is just exactly the vector of these coefficients here, of these coordinates. So in this case, this is a vector 1, 2. And for example, if you would write down the coordinate vector of a basis element, for example b1, with respect to this basis, then this would be just the vector 1, 0, because this is 1 times b1 plus 0 times b2. And so this we want to introduce today, and also we want to write down the matrix of a linear map with respect to a basis. And we will later see why this makes sense, because in certain bases we can describe linear maps in a nicer way. For example, if you consider the linear map which projects onto a line spanned by a vector u, then the matrix might look quite complicated. But if we choose a nice basis where this u, for example, is one of the basis elements, then we will see that the matrix with respect to this basis, whatever this means, looks quite simple. Okay, but first let's talk about these coordinates, and for this we will first introduce the so-called coordinate map. So let B with m elements b1 up to bm a basis of some subspace V, which is a subspace of Rn. Then first notice we know that this m is smaller than n, but we don't care about this now. And so what we then define is a so-called coordinate map, which now goes from Rm. So this m here is the dimension of the subspace V. So notice the dimension of V is m, because the basis element, we have m basis elements, and the map CB is now a map from Rm to Rn, and it sends a vector of numbers lambda 1 up to lambda m to this linear combination of these basis elements. Okay, and so here in the example before, with this subspace here, we would have that CB is a map from R2 to R3, sending lambda 1, lambda 2, exactly to this lambda 1 times B1 plus lambda 2 times B2. Okay, so for example we see here that this 1, 2 gets sent exactly to the x. Okay, so and the first statement about this coordinate map is the following. So let again be a basis of m elements of some subspace V. Then the first statement is that this coordinate map is bijective. And but here we need to be a little bit careful. So here in the definition, CB is a map from Rm to Rn. Well, what is the image here of this map? Well, we take the image is given by all linear combination of these vectors b1 up to bm. So therefore the image is exactly the span of these vectors, and the span of these vectors is exactly V, because these vectors are a basis of the space V. So the image here of this map is exactly V, and therefore if we consider this map now as a map from Rm to V, then this map is actually bijective. So clearly it's surjective, because as we will see in the proof, or as I just mentioned, the image is exactly the span of these vectors B, but the statement here is that it's also injective. And then the second statement, which is actually just a reformulation of the first statement, is that for any vector x in the subspace V, we can find unique numbers lambda 1 up to lambda m, such that this x is the linear combination of these basis elements. Okay, so let's prove this. So for number 1, well, the image of CB is, as I said, exactly the span of these vectors, but the span of these vectors is exactly V, because these are a basis of the subspace V, and one condition is that they span the space. So therefore it's surjective, and if I have an element lambda in the kernel of this map, so let's say lambda is the vector lambda 1 up to lambda m, then what does this mean? Well, this means that CB of lambda is 0, and CB of lambda is exactly this linear combination here of these vectors. And the statement is that this is 0. So this is CB of lambda equals 0, meaning this is an element in the kernel. But now we know, because these B1 up to Bm, they are a basis, and therefore they are linearly independent. And then we learned linearly independent means whenever I have a linear combination of these vectors which is 0, then this means these coefficients need to be 0. So therefore this vector lambda 1 up to lambda m needs to be the 0 vector. And therefore, the statement is, if I have an element in the kernel, then this element needs to be 0. And therefore, the kernel is just given by the set which contains just the 0 vector. And then we learned, so this is theorem 8.7, that if the kernel of a linear map is just the 0 vector, then this linear map is injective. And therefore it's surjective and injective, and therefore this map is bijective. And number 2 is just a reformulation of this statement here, namely this for all. So for all elements here, we can find lambdas here. This is just a statement that this is surjective, because the image is everything. Therefore, for any element in V, I can find an element in Rm such that CB of this element is this X here. So this is just the statement of being surjective. And this uniqueness here is exactly that, the statement that this is injective. So there are no two different lambdas which gets mapped to the same element. And therefore number 1 is exactly equivalent to number 2 here. Okay, and so therefore if we have a basis and we have some element in the subspace, then we can assign to this element these unique numbers, lambda 1 up to lambda m, and as I said at the beginning, these numbers will be called coordinates. So this is the next definition. So if you have a basis of some subspace V and some element in this space which can be written uniquely as this linear combination in these basis elements, then these numbers lambda 1 up to lambda m are the coordinates of this element x in the basis B. So here it's really important, if we change the basis, if we choose a different basis, then of course also these numbers change. And then if we write these numbers into a vector, then this is what we call the coordinate vector of x, again with respect to the basis B. And the notation is that we write this brackets here around x, B. So this is just a vector where we write down these numbers. But also this is the inverse of the coordinate map of this vector x, because the coordinate map here goes in this direction, so it sends a vector lambda 1 up to lambda m exactly to this linear combination. Therefore, if I start here with an element in V, x, and I want to know these lambdas, then what I need to take is the inverse, so going in the other direction. So therefore the coordinate vector is just another way of writing the inverse of the coordinate map. So the inverse of the coordinate map gives us, for a given element x in a subspace, gives us its coordinates with respect to the spaces. Okay, so let's do a few examples for this. So first example is if we consider Rn. Rn is also a subspace of Rn, and this standard basis consisting of these vectors 1, 0, 0 up to 0, 0, 0, 1. So this E1 up to En is a basis of Rn. So we can ask ourselves, if I take an element x in Rn, what is the coordinate vector of this vector with respect to the standard basis? Well, in this case, I need to ask myself, how can I write an arbitrary vector here as a linear combination in these basis elements here? So if let's say I have a vector x1 up to xn, well, how can I write this vector as a linear combination of these? Well, I take x1 times e1 plus x2 times e2 up to xn times en. Therefore, the entries here are exactly x1 up to xn. So in this case, it's just the vector x itself. So the coordinate vector of some vector x in Rn with respect to the standard basis is just the same vector. So in this case, this is maybe not so interesting. So, but now let's consider the following example here. So let's take these two vectors in R3. So I have B1 is 1, 0, minus 1. And I take the vector B2, which is 1, 2, 3. And first you can check these two vectors are linearly independent, because one of them is, so for example, B1 is not a multiple of B2. So therefore, if I consider the span of these two vectors, then these two vectors form a basis of this subspace V. And now we can ask ourselves, is the vector 3, 4, 5 an element in V? And if this is the case, then the notion of the coordinate vector makes sense. So we can ask ourselves, what is the coordinate vector of this element with respect to this basis here? So how do we answer these two questions? Well, we can do it in one step. Namely, what we need to show is if this vector can be written as a linear combination of these two vectors. And if we know the linear combination, then the coefficients in this linear combination are the entries of this vector here. So first, maybe here, so this vector will be an element in R2, even though, so these are elements in R3, so this here is again a plane, but this is a space of dimension 2, so this is 2, and therefore the size of the coordinate vector is also a vector in R2. So, so we need to solve, to answer this question, to solve how to write x as lambda 1 times b1 plus lambda 2 times b2. And this is just a linear equation where on the left hand side, well, we write these two vectors here, b1, b2. In the augmented matrix, the right hand side is the vector x. So this here is just a 1, 0, minus 1, 1, 2, 3, and 3, 4, 5. And then we play our usual game and bring this on row-reduced echelon form. So here we add this to this. So here we have 1, 1, 3, 0, 2, 4. And here we have a 0. And here we have a 4. And here we have a 8. And now we can subtract this twice from there. And we will see we get zeros here. And then we can divide this by 2. So first subtract 2 times this from there. And then divide by 1/2. Divide by 2. So we have 1, 1, 3, 0, 1, 2, and 0, 0, 0. And then in the last step, we subtract this one from here to get rid of this. So minus 1 times here to there. 1, 0, 0, 1, 0, 0. And 3 minus 2 is usually 1. And we get this here. And this is the row-reduced echelon form of this augmented matrix here. And therefore we can read off the solution. So first of all, we see we have exactly one solution, because this is what we showed before, that any vector, I mean, if this is in the space, then there's there we can just find unique lambda 1 and lambda 2. So this has to do with the fact that these vectors b1 and b2 are linearly independent. And we see the solution is lambda 1 equals 1 and lambda 2 equals 2. So in this case, the result is that x equals 1 times b1 plus 2 times b2. And we can check here, well, if I take this plus 2 times this, then you see we get exactly this vector here. So therefore, the coordinate vector of x with respect to the basis b is the vector 1, 2. And now I want to draw a little picture to make this a little bit more clear. So here in this picture, so this is now, I try to draw this in R3. So here we see the vector b1. So maybe we bring this down here. So here the vector b1 was going 1 there, and then 0 in this direction, and then just 1 down. So this here is b1. And then the blue vector here is going 1 there, going 2 there, and then going 3 up, which is roughly there. And then the space V is spanned by these two vectors. And what we showed now is that, well, maybe the scaling is not nice here, but we showed that the vector x here is, we take 1 times the vector b1, and then we take 2 times the vector b2, and then we get this point here. And this coordinate vector here, so this is an element in R2. So let's draw here a picture of R2, where this lives. So 1, 2. So let's draw here this vector here. So this is the vector 1, 2. And so, and here we can also draw maybe the vector. So this is 1, 0, so E1. And here this is 0, 1 and 1, 0. And so what this coordinate map is now the map. So the CB going from R2 to here. So what this basically does is, well, a plane is R2, but in some sense embedded in 3 dimensions and maybe stretched a little bit. So you see here that if you take this R2 here and you stretch it a little bit, then you get this picture here. So this this 1, 2 here gets mapped to this x here. So this here is the coordinate vector of x, and if I apply CB to this coordinate vector, then I get exactly x. And these things here are the standard basis. So the vector 0, 1, this gets mapped exactly to b2, and this vector here gets mapped exactly to b1. Because CB just sends a vector 1, 0 to 1 times lambda 1, b1 plus 0 times b2. So with this just gives b1. And this here gets mapped to 0 times b1 plus 1 times b2. So this just gives b2. So you could think of this coordinate map CB just, if I have some subspace of dimension m, then I start in Rm, and this coordinate map somehow embeds this m-dimensional space into Rn. So here this Rn is R3, and this m in this case is R2. Okay, so this is the example. And now some easy facts about the coordinate vector. So let again be a basis of some subspace V, and now consider 2 elements x and y in the subspace V and some real number mu. Then the statement is that if I add these 2 vectors in the subspace V and take then the coordinate vector, so here x and y are elements in Rn, and the coordinate vector here is an element in Rm. Then the statement is, this is the same as taking first the coordinate vector of both of them and then add them together in Rm. So here this plus is in Rn and this plus here is in Rn. And also the statement here is that if I multiply with a scalar in Rm and in Rn and then take the coordinate vector, this is the same as first taking coordinate vector and then scaling. And also here the statement, the coordinate vector of the 0 vector. So remember, the subspace always contains the 0 vector, and the coordinate vector of this is always 0, which makes sense because 0 vector means if the coordinate vector is 0, this means if I write it in terms of the base, it's 0 times b1 plus 0 times b2 and so on. And here it's again important to notice that these two zeros are two different zeros. So this zero here is the zero vector in Rn, and this zero here is the zero vector in Rn. But as I mentioned a lot of times, if we write 0, we always mean the zero vector in the correct space. And the proof of this, well, if you look at this, you might say, oh, well, this looks like the condition of a linear map. And this is true because, as we saw before, the coordinate vector is exactly just the inverse of the coordinate map. So the coordinate vector of something is given by the inverse of the coordinate map. And we learned CB, the coordinate map, is a linear map. And we also learned that if we take the inverse of a linear map, then this is again a linear map. And therefore, because CB, the inverse of CB is linear, these statements follow, because these are exactly the condition of CB inverse being linear. So this is the proof of this. Okay. Okay, so now what we want to do now is we want to consider linear maps. And so what we want to do is, after fixing a basis in our space, so let's say we have some linear map between Rn and Rm, then we want to choose spaces in these two, in Rn and Rm, and we want to write down this linear map with respect to these spaces. And so in the example later, maybe I hope it becomes clear what I mean by this. So, but first what we need to define is the following. So if I have a basis of Rn, so I need to have n vectors which are linearly independent, then the so-called change of basis matrix associated with this basis B is the following. So we denote it by SB, and this is just the matrix associated to the linear map CB. And this just means, because CB is a map which sends a vector lambda 1 up to lambda n to the linear combination lambda 1 times b1 and so on. So this just means that the columns of this matrix here is given by these basis vectors. So this here is an n by n matrix. Okay, so first noticed, so a remark, that this matrix, so this is a square matrix, and the columns of this matrix are linearly independent, because this is a basis, and therefore we learned that this matrix is invertible. So this is the first statement, and the second statement is that what we already saw, that if I have an element x in Rn, and if I multiply this change of basis matrix with the coordinate vector of x with respect to the spaces, well, what is this? So if I multiply with the matrix SB, then this is just the same as applying the map CB, because SB is defined to be the matrix of CB, and the coordinate vector of some vector with respect to a basis B is given by the inverse of the coordinate map. So therefore, this just gives the vector x. So if I have a vector in Rn, and I write down the coordinate vector with respect to some basis B, if I multiply with this change of basis matrix, what I get back is the original vector x. Okay, and now comes what I said before, namely we want to consider linear maps, and we want to write down the matrix of a linear map with respect to a basis. And this is the following, which maybe on the first look looks a little bit complicated, and it's always confusing if you see it the first time, but I hope in the example it becomes clear why this is actually an important concept. So we learned before what it means to write down the basis of a matrix. So what this was, just the columns were given by the images of this matrix, of these vectors e1 up to en. But what we want to do now, we want to generalize this idea. So what we defined before was the matrix of a linear map with respect to the standard basis. Okay, but let's first define this. So let F be a linear map from Rn to Rm. And now let's choose a basis in Rn, which we call B1. And let's choose a basis in in Rm, which we call B2. And then what we define is a matrix of F with respect to B1 and B2. And we use this notation here. So we write F in these brackets. So what we defined before was without these B1 and B2. So we did define what it means to write down the matrix of a linear map. But now we write B1 on the bottom and B2 here on the top. And the definition of this is that this is the matrix of this linear map here, where this linear map is given by the composition of the coordinate map CB1. Then we take F, and then we take CB2 inverse. So let me draw a diagram here. So we start with the linear map F. So F is a linear map from Rn to Rm. And B1 is a basis of Rn. So therefore, we have the coordinate map CB1, which goes from Rn to Rn. And we also have the coordinate map CB2, which goes from Rm to Rm. And what this matrix here now is the matrix of this map here, because this map here is we start in Rn, then take CB1, take F, and then we take CB2 inverse. So here is CB2 inverse. So this map here is CB1, then F, and then CB2 inverse. And so this is a linear map from Rn to Rm, for which we know what we mean by the matrix of this. And this is what we will denote by this matrix here, F, B1, B2. But in the most cases, we will not have two different bases. So in the cases we will consider the most, we will actually consider a map from Rn to Rn, and B1 will also be the same as B2. So in this case, if n equals m and these two bases are the same, we will just introduce this notation here, where we just write these f in brackets and then write B1 here on the bottom. And yeah. Okay. So of course we will do an example for this, but what is the interpretation of this? So if we start with a linear map F, so we know what to do with a vector in Rn, we can apply F and land here in Rm. But now we also learned what it means to write down the coordinate vector with respect to a basis. So B1 is a basis of Rn. So if I have an element here, x in Rn, then I can write down the coordinate vector of x. So here I can write down the coordinate vector of x with respect to the basis B1. So this is living here. And also if I have here some element y, I could also write down here the coordinate vector y with respect to the basis B2. So, so what this matrix here with respect to the basis B1 and B2 tells us is that if I have an element in my space and I have the coordinate vector, then if I multiply with this matrix here, then what I get as an output is the coordinate vector. Maybe make it clearer here. So let's say if I have f of x, then I have an element here, and so the coordinate vector of f of x with respect to the space is here. So if I start with a coordinate vector of some element and I apply this matrix with respect to B1, so I multiply this matrix here with a vector, coordinate vector with respect to the basis B1, and the output will be a coordinate vector with respect to the basis B2. So yeah, and we will later see that this is actually, for some linear maps, it's easier to understand this matrix here, and then later we can write down the matrix for f. For example, if I have a projection, as I said at the beginning, to some span of a vector u, then if I consider the basis where this u is an element, then with respect to this basis, it's quite easy what this projection does for this basis element, because in this case this basis element just stays the same because u is on the line spanned by u. So therefore we can write down this matrix here quite easily. Okay, but first some statements for this matrix of f. So again, let's take a linear map from Rn to Rm, and I have a basis B1 of Rn and a basis B2 of Rm. Then the first statement is that this matrix here, which we just defined, is given as a product of these three matrices, where this SB1 is this change of basis matrix with respect to the basis B1, F is just the matrix of F, and SB2 is the change of basis matrix for this basis B2, and here we take its inverse. And the second statement is that, which will follow from this, that if B1 is given by the basis B1 up to Bn, then this matrix here is just given by the matrix where the columns, the first column is the coordinate vector of f with respect to the basis B2 up to, and here we have the coordinate vector of f Bn with respect to the basis B2. So let's prove this. So, well, what was this matrix here? So this was the matrix, so by definition, given by the composition of these three maps. And then we learned that if we compose linear maps, then the corresponding matrix is given by the product of the matrices of these maps. So here we take the matrix of this map times the matrix of F times the matrix of this map. But this change of basis matrix was exactly defined as the matrix of the coordinate map. So this here is exactly SB1, where this here is just the matrix of F, and this here is the matrix of the inverse of the coordinate map. But here we also learned that if I take the matrix of an inverse of a linear map, then I can put this inverse outside, meaning I can consider the inverse of the matrix of this guy here, and this is exactly SB2. So this is the inverse of SB2. And this is exactly the first statement. And for this statement here, so how do we write down, what is F B1, B2? So if I multiply this with this vector EI, so the ith column of this matrix here. So if I have a matrix, in general, if I multiply with the vector EI, so if I multiply with E1, I get the first column. If I multiply with E2, I get the second column. So if I multiply with EI, I get the ith column. So here at position I, we now want to see what is the column. So this we get by multiplying with this. And, well, but this is just by definition. So we need to apply CB1, EI, then we apply F, and then we apply CB2 inverse to this. And what is the coordinate map CB1 applied to EI, where this is just the vector BI. So here, because remember the coordinate map just sends a vector to the corresponding linear combination of the basis elements, but this vector EI has zeros everywhere, but at the position I we have a 1, and this just means you take 1 times B1, so therefore this part here is just BI. So this is CB2 inverse of F BI. But the inverse of the coordinate map is exactly the coordinate vector. And this is what we wanted to show, because here this is now the ith column here, and this is exactly the statement of this proposition here. Okay, but now let's do some examples to make these notations a little bit clearer. So this is example 24. So first, let's take a linear map F from Rn to Rm, and now choose in both sides the standard basis. So then, first, what we want to see is what is the coordinate, the matrix of F with respect to the basis B1 and B2. Well, we saw that for this we need to, we can calculate it like this here. So what is SB1? Well, SB1 is the matrix of CB1, and CB1, the entries of this matrix here are exactly these vectors here. So this is just the identity matrix IN, and SB2 is the identity matrix IM. So therefore, this here is just the inverse of IN, which is IM, times the matrix of F, times the inverse of IN. So this is just the matrix of F. So this is what I said before, that so far the matrix of a linear map F, which we defined a long time ago, this was always the matrix of F with respect to the standard basis. So we, if we multiply this linear map, we multiply with the coordinate vector with respect to the standard basis, which was just exactly the same vector, and the output was again then the output with respect to the standard basis, which was just the output of this linear map F. Okay, but now let's do a more interesting example, namely the one I mentioned several times. So let's consider the projection to a line spanned by a vector u, which we denoted by pu. So here u is a vector -3 and 2. So you see here in the picture, so this is in R2. The image of this linear map here is given by the line here. So maybe recall what this map does. If I have some x here, then this map sends x to the projection onto this line. So this here is pu of x. And now, so first of all, so the image of pu, so this is the span of u. And what is the kernel? Well, the kernel are all elements which gets mapped to 0, and therefore these are the elements which are on this line here, which is perpendicular to the line spanned by u. And so here the kernel of pu is so these are all elements in R2 which are orthogonal to U. And in this case, we can see that, for example, we can span this line here by this vector v here, which is a vector 2, 3. Yeah, you can check that if you take the dot product of the vector 2, 3 with minus 3, 2, then this dot product is 0, and all multiples of this vector here are perpendicular to this line spanned by U. So this vector we want to call V. And now first notice these two vectors, U and V, are linearly independent, and they also span the whole space. So if we write down B now, let's take the basis which consists of the vector U and V. So this is a basis of R2. So in other words, any point here in R2 can be written as a unique linear combination of these vectors U and V. And now we can ask ourselves, what is the matrix of this projection with respect to this basis here? So, and for this, so let's go back here. So what we want to calculate now is this matrix here, and we take the case where B1 equals B2. So what we need to calculate is we need to apply f to the first basis element. In our example it's U. Then this will give some result, and then we need to calculate the coordinate vector with respect to the basis. So we need to ask again, how can we write this result as a linear combination of U and V? And then the second column will be, we need to apply the linear map to the second basis vector, which in our example is the vector V. This will give a result, and then we ask ourselves, how can we write this result again as a linear combination of our basis vector U and V? And in this example it's really simple, because what is Pu of U? Well, Pu is the projection onto the line spanned by U. Therefore, Pu of U is just U, because it doesn't do anything to U. And Pu of V, well, what is Pu of V? If I apply Pu to V, then this gets mapped to 0, so this is just 0. So therefore, in this case, it's really easy to write down what the matrix of the projection with respect to this basis is. So recall, this here is just a notation for we go from this basis to this basis. So in this case, it's the same. So what we need to calculate is, the first column is Pu of U, and then we take the coordinate vector with respect to the basis B. And the second entry is Pu of V with respect, and then the coordinate vector with respect to the basis B. So this here, Pu of U is U, and how can I write U as a linear combination of U and V? Well, it's 1 times U plus 0 times V. And Pu of V is 0. How can I write this as a linear combination of these vectors? Well, it's 0 times U plus 0 times V. And therefore, we see the matrix of the projection onto the line spanned by U with respect to this basis here is just this simple matrix here. Yeah? So you can directly read off what this matrix here does, because you see that the first basis vector just stays the same, and the second basis vector, which, because here everything is 0, just gets sent to 0. And with this we can also now calculate the matrix of Pu. So so recall by this proposition we had before, the matrix of Pu with respect to a basis B, so this guy here, is SB inverse of the matrix of PU times SB. So what is SB? So SB is in our case the change of basis matrix. So this just means we write here the vector u and here the vector v. So in this case it's minus 3, 2 and 2, 3. And so what we have now is this here. We have this here. And the inverse, SB inverse, we can also calculate. So this is just inverting this matrix here. So this I will just give you for free. So it's minus 3, 13, 2, 13, 2, 13, 3 over 13. Because we learned how to calculate the inverse of the matrix here. And so we now have this, and we have this. So we can calculate PU now. So the matrix of this projection onto U, well, we can first multiply with the inverse from the right. So here we have SB inverse, then PU with respect to the basis B, this here, and here from the left we multiply with SB. So this here is now just this here where we solve for this matrix here. So first from the right we take the inverse SB to get rid of this, and then from the left we multiply with SB to get rid of this. And this we can now write down, and because I'm lazy I just copy this here. So this is this. Oops. I'm too stupid. So this, and in the middle is this simple matrix here, this 1, 0, 0, 0. And in the end you can multiply this out, and what you get should be this here. So this you can check by yourself. And therefore we see the matrix of this projection onto the line spanned by U is given by this matrix here. And this you can compare with your homework 4, exercise 1, the second part. In this homework you gave a formula for the matrix of PU in general, and you will see if you use this U in this example you get exactly this matrix here. But notice here that to calculate this matrix we basically just used the geometric interpretation of this map, because with this basis here it was quite easy to write down what this linear map does to these basis elements, because it's a projection onto U, so therefore just U stays the same and V is orthogonal, and therefore V gets mapped to 0, and therefore it was really simple to write down this matrix here. And writing down this change of basis matrix is also quite simple, because it just means we write down these basis elements in this matrix here. And well, then it needs a little bit calculation, but this is a straightforward calculation. If you have a matrix which is invertible, you can always straightforward calculate the inverse, and then multiplying these three matrices we get back our the matrix of this PU here. So now if you want to know what happens to this purple X here, we can multiply it with this matrix here. I mean, of course, we could also write X as a linear combination of U and V, and then take the coordinate vector of X and multiply it with this matrix here. And then this will give some output, some numbers, and then these two numbers we can take and write down the linear combination in U and V, and this should give the same result. So this then should give this point here. Okay, so this is the second example, and now the third example. So here in this example, we already knew the answer to this question here, because you already calculated the the matrix of this projection in general. But now we will do an example where we didn't do this before, but we can do again the same strategy like here. So there's a really simple geometric interpretation, and we just need to find the right basis, and then we can write down the matrix with respect to this basis, and then we can do this calculation to get back the matrix of the linear map. So, and the linear map we are considering is the following. It's from R3 to R3, and this will be a reflection in the plane. So what I mean by this, if I have a plane and I take a point, I want to reflect on the other side. So far we just did this for a line. So we defined what it means for a line in R3 to take the reflection along the line. But it also makes sense to take a point and then reflect along a plane. So in this case, what we want to consider is this plane here, U, which is the span of these two vectors. And the goal is to determine the matrix of the linear map F, which takes the reflection in this plane U here. So what is the strategy? Well, the idea is find a good basis. And then, so let's say find a good basis B, and then calculate the matrix of F with respect to this basis. And then again, as before, calculate the matrix of F by multiplying with the change of basis matrix and the inverse. And what do I mean by good here? By good, I mean is we want to find a basis for which we can understand this linear map F quite simple. So for example, two candidates for a basis in R3. So U1 and U2 should at least be contained in this good basis, because if I reflect along this plane here, then f of U1 should be just U1 because it's on top of the plane, and f of U2 should also be just U2 because it's also on the plane. So what we want to find is something which is orthogonal to the plane. This will be our third basis vector, because this vector we know the reflection of this will be just multiplying by -1. Okay, so let's do this. So here I prepared a picture to what I want to find now. Oops. So here we now have the plane spanned by U1 and U2. And what I want to find is a vector v, which is orthogonal to U1 and U2. And the basis I want to write down then is U1, U2, and v. Okay, so find v in R3 with U1 dot product v equals U2 dot product v equals 0. And if this vector v is v1, v2, v3, then what this means is, well, u1 is just a vector 1, 1, 0. So the first condition is that v1 plus v2 equals 0, because this here is just u1 times v2. And this here u2 is 0, 1, 1. So this will give v2 plus v3 equals 0. So we want to solve this linear system here. And, well, we did this several times. You can check that one solution, there are infinitely many, because you know that any element here on this line is a solution. But one simple solution here is, for example, 1 minus 1, 1. You can check that the vector 1 minus 1, 1 is orthogonal to 1, 1, 0 and also orthogonal to 0, 1, 1. And so our basis will be now the following. So 1, 1, 0, u1, 0, 1, 1, u2, and 1, minus 1, 1, v. And you can check that this is actually a basis. It's a basis of R3. So you need to check that they are linearly independent, but this I will leave out now. And but what I want to write down now is the matrix of this linear map with respect to this basis here. And to do this, we again need to calculate f of these basis elements. So what is f of u1? Well, because u1 is on the plane, so reflection is just u1. What is f of u2? Well, it's just u2 because it's also on the plane. And f of v should be minus v. Because v is orthogonal to the plane and reflection means I want to reflect, so it should be minus v. And therefore, to write down now the matrix of f with respect to the basis b, I want to write down what is f of u1 and then the coordinate vector with respect to the basis b, f of u2, coordinate vector, and f of v, coordinate vector with respect to the basis b. But this is easy because f of u1 is just u1, so therefore the coordinate vector, we need to answer the question, how can I write u1 as a linear combination of u1, u2 and v? Well, but this is just 1, 0, 0. Similar here, u2 is just 0 times u1, 1 times u2, 0 times v. And minus v is 0 times u1, 0 times u2, and minus 1 times v. And therefore, we have the matrix of f with respect to this basis p. And this was quite simple to write down. And now, again, we consider the change of basis matrix. This is SB, so this S entries just has these three vectors, u1, u2, and v. So this is 1, 1, 0, 0, 1, 1, and 0, minus 1, 1. And SB inverse, well, for this you need to calculate the inverse of this matrix here, which I again just give you for free, which should be 2, minus 1, 1, 1, 1, minus 1, minus 1, 2, 1. And now the matrix of f with the same argument as before can be calculated as SB times the matrix of f with respect to the basis b times SB inverse. So we have all ingredients here, so we have this matrix here, and this matrix is given by this matrix here, which we derived by understanding the behavior of this map with respect to the basis b. And in the end, you will end up with this a little bit complicated matrix here. So if you multiply everything out, you will get this matrix here, and this matrix is the matrix of this linear map f. So this, if you multiply a vector in R3 with this matrix here, then this will reflect along the plane which is spanned by these two vectors. And if you don't do this change of basis thing here and write down the matrix of f with respect to this basis, then it might be quite difficult to answer this question here. Okay, and this is everything for today. So next time we will talk about some special bases which are so-called orthonormal basis, which is basically just the basis of a space where everything is orthogonal to each other, and we will see why this is a nice concept. See you then.